good morning or good afternoon or good evening, depending on where you are, right? So nowadays, these events are global. We are delighted to welcome Alessio Figalli to our MoD colloquium, MoD lectures. So our university, Friedrich-Alexander-Universität in Erlangen-Nürnberg, is not only running activity in mathematics, but actually we have a very strong agenda in engineering and also with applications to medicine, the medical valley. And then the university decided to gather a number of us on this research center, Mathematics of Data, because we are, of course, as many other institutions, also evolving into the field of data science, artificial intelligence, and machine learning, not only from the math perspective, but also from the applications. And one of the activities we try to promote is to run once every, say, quarter or so, one of these MoD lectures, trying to bring the best people in our field. Today, we are very honored that Alessio accepted to deliver this talk, this time online. I think he's someone that nobody needs many details. You can have a look in the Wikipedia. Alessio was born in '84 in Rome, so he's still a very, very young mathematician. Despite of this, his records and trajectory are very impressive. He was a student with Luigi Ambrosio and Cedric Villani. He has been also a close collaborator of Luis Caffarelli, recent Abel Prize winner. And he got himself the Fields Medal a few years ago, I think in 2018. So it's already 5 years ago that he got it. For the last few years, he is a professor in ETH Zurich. And among the different topics he has developed, probably those that are better known for our community are optimal transport, Monge-Ampere equations, and free boundary problems, among other fields. And today he is precisely lecturing on free boundary problems that, as you know, is one of these classical topics in analysis of PDEs that is certainly one of the most challenging and on which still, despite of the great progress and contributions in particular by Alessio, there is still so much to be done. So this is why we believe that the topic chosen by Alessio for this lecture is particularly appropriate. So Alessio, thank you again. And we are ready to listen to you. Thank you.
Thank you very much, Eric. It's really, really a pleasure for me to deliver this lecture. Yeah, today I would like to talk about the obstacle problem, which is a very classical free boundary problem. I mean, many of you already know it, but I prefer to start really from the beginning and really have, I mean, you don't need any knowledge of it. I will guide you through this problem and guide you through the free boundary regularity. That's the goal of this lecture. So what is the obstacle problem? There are many ways to introduce it. It models a lot of different phenomena. I will take away an approach which is kind of convenient for me to get immediately to back very quickly to the equations that we have to solve. And it starts as follows. Let's say that I have a wire. Okay, so this is a metal wire. So this is a wire that I assume it's a graph of some function over some domain. So let's say that I have some domain here downstairs that I denote by omega. And then let's say I have some function. This wire can be seen as the graph of some function. So I have some function f defined on the boundary omega with values in, let's say, 0 plus infinity. So I assume the function to be positive. And my wire is the graph of f, of this function f. Okay. So what do I do? My metal wire is here in the space, lying in my space, and I'm going to attach an elastic membrane to it. So I will have now an elastic membrane that is gonna be attached to my wire. So this is my elastic membrane. And so my elastic membrane is what? Is again a graph. So this is a graph on some function u, where now u is a function from omega into r. And the fact that u is attached to the wire means that u restricted to the boundary of omega is equal to f. So this is my boundary condition. Now, my goal is to find the equilibrium configuration of an elastic membrane attached to a wire. So let me start by steps. So the first step is, if you want, just basic linear elasticity. So step 1, point. What I'm going to do is going to minimize an energy. And the energy I'm going to put, so I will consider all functions that are equal to f on the boundary. So this is the boundary condition. And then I minimize over omega the Dirichlet energy, gradient square. Okay. So this corresponds to a linear elastic energy of my membrane. So it's a very simplified model. And you ask yourself, what can I say about the minimizer? Well, we all know what to do here, because when you have so first of all, it's very easy to prove that the minimizer exists. It is unique. And now if U is a minimizer, what would you do? You would just say, well, then the energy, then it means that for every epsilon and for every, let's say, phi, some smooth and compactly supported function in omega, I have that the energy of U is less or equal than the energy of a competitor. So a competitor will be something like U plus epsilon phi. So I'm going to perturb my minimizer by some smooth function. And then I know that my energy is minimized at epsilon equals 0. So then what you do is that you differentiate this relation at epsilon equals 0, and you discover that the integral of grad U times grad phi is equal to 0. But this means, in the sense of distribution, that the Laplacian of U is 0, so U is harmonic. Okay. So this would be, a very simple model. Now let's make it slightly more complicated. Let's say, okay, this is my model, but let me assume now that I have gravity. So let's add the gravity. So gravity is pushing down my membrane. My membrane will tend to bend. So my energy now will be grad U square over 2 plus gravitational potential. So it's G times U. So G is a constant, and then U is the height of my membrane. Let's assume we are mathematicians, so we just say, okay, the G, I can set it to 1. Doesn't matter, okay? So then my energy is grad U square over 2 plus U. You repeat the argument before. U is a minimizer, so U is less. The energy of U is less or equal than the energy of U plus epsilon phi. You differentiate, same computations, and you discover that in this case, the Laplacian of U is identically 1. So this is the equilibrium configuration. So what is the difference between the gravity and no-gravity? In the gravity case, in the no-gravity case, my membrane is expected to be, tend to be rather flat, but as gravity is there, and gravity will make it bend. So my membrane will have more of a configuration, like if this is my wire, my membrane will tend to bend more like this, my elastic membrane. But now I want to talk about obstacle problem. So let's add an obstacle. The way I'm going to add an obstacle is in a very simple way, by just imposing that so I told you, F was non-negative, so my membrane was lying in the positive half space, up in the upper half space, right? So I have my, if I think that this is my Rn and this is R, this is my domain omega, right? And my wire was on the top, was above, so something like here, right? This was my wire, and now I was attaching the membrane to it. I was attaching my elastic membrane. Now, because of gravity, my membrane will tend to bend down, right? And a priori it could bend more or less, it depends. I mean, it will bend a lot. But now I'm gonna force my elastic membrane not to cross my plane xn plus 1 equals 0. So this plane, this Rn, is xn plus 1 equals 0. This corresponds to the in Rn plus 1. And now what I'm going to do is to minimize the same as before, grad u square over 2 plus u over omega. But I will not only ask my function to be attached to the wire, but I will also ask my function to be non-negative. Okay, so my function is not allowed to go down. So it means that my elastic membrane is attached to the wire, but it cannot cross xn plus 1 equals 0, that you can think like a table. So my elastic membrane is above a table. If the membrane is very high, you will not see the table, but as I lower my boundary, my wire, and I make it closer and closer to the table, at some moment my elastic membrane will touch the table and there will be a contact region. So this is my contact region, u equals 0. And then there will be a region where u is positive. Okay, so what is the PD in this case? Here you need to work a bit more. So what I did before, where you just add epsilon phi, blah, so as before, so where you just say, oh, the energy of u is less or equal than the energy of u plus epsilon phi. Well, it doesn't work as easily because you see that here now you have a constraint. So you have this constraint, which is this here, u greater or equal than 0. So any variation you do, if you do u plus epsilon phi, you need to make sure that this is still admissible. So you have to be careful with the Euler-Lagrange equations. But one can do it. It's not too complicated, but it's not trivial either. And the PD that you get, I will tell you immediately, is Laplacian of u equal characteristic of u positive. This is the PD. This is not so surprising because what does it mean this? Sorry, I erased by mistake. What does it mean? This means the following. So the characteristic of a set, remember, is the function which is 0 outside A and 1 inside A. So this means that if I look at my domain omega, let's say, and let's say here u is 0, so this is u equals 0, and here is where u is positive. So where u is positive, the Laplacian of u is equal to 1. Because the characteristic function will be 1 there, which is natural because where u is positive is like if the obstacle is not playing any role, and so the PD is the same as if there were no obstacle. So this is the same PD, Laplacian u equal 1 is the same PD when you only have gravity and no obstacle. Of course, this is more delicate because then you have to be careful what happens here, right? When you approach the boundary, the interface. And the PD tells me that the Laplacian is the characteristic of this set. So it will be 1 where u is positive and 0 where u is 0. Okay. So this is the PD. So from now on, I will focus on this equation. And this is the obstacle problem. Okay. So now we start our questions. So the question that we ask ourselves are two. First question is, what can we say about the regularity of u? And second question, then, what can we say about the free boundary? Notice that we are used in PDEs, like when you have harmonic functions, that the solution to smooth PDEs are usually very smooth, like solution to harmonic equation are infinity, even analytic. Now, in this case, so question 1, how smooth is u? So the remark you can make immediately is that the Laplacian of u is the characteristic of u is the characteristic of u positive, which is not a continuous function, right? Because it jumps between 0 and 1, depending whether you are in 0 region or in the positivity region. So this implies in particular that the action of u is not C0, right? So u is not C2 for free. Cannot be C2. Well, the answer to this question, answer to question 1, was given in the 1960s. There have been many different contributions. 1960s, sorry. 1960s, by Frese and then many other important mathematicians. And what they proved is that essentially, the solution is not C2, but it as close as it could to be C2, which is the following theorem: U is C11. What does it mean? It means that U, that is, U is differentiable twice, and the second derivatives of U are L infinity. So the action is not continuous, but the action is bounded. So this is optimal, of course, because of what I just mentioned, that continuity is not possible. So you can only hope for bounded action. Now, question 2 is how smooth is the free boundary? So the free boundary is the boundary of this contact region. So let's say the boundary of U positive, right? So it's the boundary of this interface. We call it free boundary because it's a boundary, but it's not a boundary that is given by as a datum. It's part of the problem itself. So this is really our challenge: understand the regularity of this free boundary. So about question 2, there have been many partial results here, and now we will start a nice history. So the first, I would say, very important result in this direction is a theorem by Kinderlehrer and Nirenberg in 1977. And the result of Kinderlehrer and Nirenberg can be thought in the spirit of Schauder theory. Schauder theory tells you if you have a solution of a PDE with some kind of nice coefficients, then the solution is smooth, as smooth as the coefficients allow it to be. So you start maybe from some solution, some datum, which is, I don't know, C0 alpha or C1 alpha, maybe the coefficients, and then you get regularity of the solution. But in Schauder theorem, there is already an initial regularity to start with. The coefficients have to be at least older continuous or something. So, for instance, it doesn't apply to measurable coefficients. So there is like, you get regularity provided you know something to start with. And here is a bit the same. The theorem goes as follows. So what Kinderlehrer and Nirenberg proved is the following theorem. Let's assume that I have such a picture, that I have a free boundary point such that the following goes. So this is my free boundary of U positive. And I assume, let's say that this is, I don't know, the origin. And I have a ball around it. So this is a ball of radius R. So this is BR. And I'm going to assume that here U is 0. Here on the top, U is positive. And then I'm going to assume that this free boundary inside the ball here, this is C1 hypersurface. Okay, so we're assuming a very nice configuration, right? So I'm going to assume that my free boundary is such that around, let's say, one of its points, there is a nice C1 hypersurface that cut my ball in two pieces. In one side, U is positive, the other side, U is 0. Okay, so this is my assumption. And then, under this assumption, then in BR over 2, let's say, so in alpha of the ball here, the free boundary is C infinity, actually analytic, if you want. Okay, so once you have a bit of regularity to start with, you have a bit of C1 regularity to start with, then you get a C infinity or analyticity. Of course, I'm telling you something very strong. I'm not telling you only that the free boundary is C1, but I'm also telling the assumption is that really you have an upper surface C1 that separates. On one side, you have the 0 set, and the other side, you have the positivity set. So it's really like a very sharp configuration, okay? So this is a sort of conditional theorem, right? So if you have this, then the free boundary is very nice. Of course, a priori you could argue, well, but what can I say about this? I mean, maybe this set of points where this theorem applies is empty, and then it doesn't tell me anything. So yeah, this is a criticism that you could make, but then luckily for us, there was Caffarelli in the game. And so Caffarelli, in his famous paper in 77, he proved the following theorem, that the free boundary is the union of two parts, reg union sing. So the free boundary is split in two pieces, okay? Piece one are regular points. What is a regular point? These are points as in Kinderler-Nuremberg. So you have a part of the free boundary that are all the points where the Kinderler-Nuremberg theorem applies, okay? And now the question is then, what is the rest? And what Caffarelli proves is that the rest is actually, he can describe it in some way. This set is a set of points such that the following holds. So if you're a singular point, then the free boundary is a very specific behavior. Oops, sorry. The free boundary behaves as follows. So I have my point, let's say my free boundary point. I take a ball around it of radius r, small radius r, drawing a large ball just to make the picture. And then I can find a direction ER on the unit sphere. So in S n-1, let's say, I don't know. This is my direction ER, such that if I draw the hyperplane orthogonal to ER, so this is ER.x equals 0, then my free boundary is trapped between two parallel hyperplanes here. So my free boundary will be something like this in it. Maybe. This will be my free boundary. This will be like, I don't know, u equals 0. And then on the side, here on the outside, let's say here, outside these two hyperplanes, u is positive. And these two hyperplanes are very close. So the let's say these two hyperplanes here, this is a little O of R. Okay, so if I look in a ball of radius R, I can find an hyperplane and then two parallel hyperplanes that are extremely close compared to the size of R, so it's a little O of R, such that the free boundary lives inside these two hyperplanes, and then outside these two hyperplanes, U is positive. Okay, so these are the singular points. And the breakthrough of Caffarelli was to prove that nothing else can happen. So either you look like this, or Kinderler-Nuremberg theorem applies. Okay, which is highly non-trivial, because I'm saying that everything else is a nice analytic piece. So let me try to give you an example to understand what this is saying, like in this picture. So think of this example in 2 dimensions. The free boundary could be this. So this is my contact region. And then here U is positive, and then here U is positive, okay? So the contact region is this union of 2 drops with a line in between, okay? Now, if I take a point here, and there exists a very small ball, such that you see on one side U is positive, here U is 0. So this is like Kinderler and Nuremberg. So all the points which are on this on the side of this drop, like these are regular ones. Instead, if you take a point, either the tip or any point here, all these points are singular. You see, the free boundary is super tiny there, and the function is very positive in a neighborhood. So in this case, the singular set is all these curves from here to here, from the 2 tabs. And then all the other points are regular. Okay. So here, this example is interesting. So that you see that the regular part is the union of 2 curves. The singular part is a segment. one segment or one curve. Let's say, well, here I didn't do it very straight, so let's say that is a one curve. So the important thing to remember from this example is that they have the same size. So it's not that regular points are more than singular points or vice versa, right? These are both one-dimensional objects. Okay, so there is no one that is bigger than the other from this example. Okay, so now the philosophy here is that the regular points are rather clear. The regular points are these points that consist of analytic surfaces, in fact, or curves, depends where you are. So what is the goal now? The goal for us, and in general for a lot of the research that has happened in the last years, is about understanding things. So understand this singular set. Okay, we want to understand how this singular set looks like. In particular, there are three questions I would like to raise. So first question, can we understand how smooth is the singular set? At the moment, the only thing we know from Caffarelli result is that around each singular point, I can find this hyperplane so that the free boundary is very close to this hyperplane. So can we say more? Question two, in the example that I just gave you, reg and sing may have the same size. Is this common? So is this a common behavior? Is this a pathological example? Whatever. And then there is a third thing, a third, let's say, point, which is more on the technical side, but actually motivates a very beautiful question, which is the following. So to study the free boundary, we perform what are called blow-ups. What does it mean? It means the following. Let's say that I have my solution. Let's say I have a ball of radius 1 here. My solution is defined here. So U goes from B1 into R. And somewhere I have my free boundary. I have my, let's say, my contact set and maybe my free boundary, and I have something like this. Okay. Now I'm going to take a point on the free boundary, let's say this one, and I want to understand what happens nearby. Okay, so I'm going to take a small ball around it, around this point, and then I'm going to zoom. Okay, when I zoom, what happens is that this ball, let me draw it directly big, will become like a ball of radius 1. And then, I don't know, in this picture, my free boundary will become like, will look something like this inside the ball. Okay, so here I had BR, and this becomes now B1 here, okay? So I'm zooming to understand what's happening. When I zoom, so what I do, something that was of scale R now becomes of scale 1. So what I've been doing is the following. Let's say that this point here, let me give it just a different color so to emphasize. This point here, my point is X bar. Let me call this point. So this is BR of X bar. So this point is X bar, okay? So how do I zoom mathematically? So here I have my function U, right? And what I do is that I consider U X bar R. It's a new function of X, which is U of X bar plus Rx over R square. Okay, so I do a translation so that X bar becomes the origin, and then I dilate so that the BR becomes B1. And the reason why I divide by R square is because then the Laplacian of U X bar R is still the characteristic of U X bar R positive. So this rescaling preserves the equation, preserves the problem. But the difference now is that my my function ux bar r, are defined in very large domains because u was defined in B1. Now, as I zoom in, the B1 becomes B1 over R. So it becomes huge. So u x bar r are defined in larger and larger balls. So if u x bar r, let's say, converges to some u0 as r tends to 0, then what I have is that u0 will be defined in the whole space now, will be a global function because it's defined on larger and larger balls. So in the limit, I get a global function. And Laplacian of u0 is the characteristic of u0 positive. So this will be a global solution. So global solution. So the question is understand them. Understand global solutions. Okay, so we want to understand all these global functions that solve the obstacle problem. Okay, but now they don't solve it in a domain, they solve it in the whole Rn. Okay, so this is the third question. So just to summarize, let me go back maybe. So question 1 is, can you understand how smooth is the singular set? Question 2, regular points and singular points may have the same size. Is this common? Question 3, can we understand global solutions to the obstacle problem? And you see, these are all related to understanding the free boundary. So there are these three beautiful problems, and there is a lot of richness behind them. So let me try to tell you a bit what you can say. So about question 1. So again, Caffarelli here, in 98, so 20 years after its first breakthrough, he proved the following thing. Sing is contained in a C1 n-1 dimensional surface. Okay, oops. Right? So he proved that the singular set, so I told you that the singular set can be n-1 dimensional, like in the example we just discussed, right? With the drops, this was a one-dimensional curve. So in dimension n would be n-1. And Caffarelli proved, oh, this singular set is contained in a C1 surface. The first question is why, the question you may have is why contained? Why is it not a C1 surface? Well, the example you can build up is the following. So you can play as follows. You start with a line, and then you start to draw the following. So you just say, oh, let me take, oh, maybe let me first 2 points. So let's say this is 0, this is 1, this is 1/3, this is 2/3. And now I'm gonna draw here a smooth set like this. And this is u equals 0, okay? Then I'm gonna split these in thirds, and then I'm gonna take again this and draw another smooth set here, u equals 0. And then you can keep doing this. And okay, and what happens in the limit? If you iterate this construction, what you can build is a solution that will have as a free boundary this. So you see, each of these is so like this is a free boundary point, and this is regular point. But the tip of this here, these are singular points. And if you iterate this construction with 1/3, 1/3, 1/3, in the end, sing is equal to Cantor 1/3. So it's a Cantor set, the usual Cantor 1/3 set that we like to, that we know, which is contained in a line. In a line. Okay, so here the singular set is made of all these extreme points of regular points, and in the end it's just a Cantor set, and everything else is regular. So the singular set is not a manifold, is not a C1 surface, but is contained in a C1 surface because, well, here is a line, so it's an analytic curve in this example, right? So I can cover the singular set with a C1 curve, but it's not that singular set is equal to a C1 curve, right? It's just a closed subset of a C1 curve. And that's the best I can prove. So the result of Caffarelli in this respect is, very powerful and very deep. The question you can ask is, okay, so the containment here, this is needed, right? So this Y is there. There is no way around it. But what about this C1? Why C1? Can I do better? So in this direction, we did a lot of work in the last years. So there has been first a paper by myself and Joachim Serra in 2019, where we proved that Sing is contained in a C11 n-1 dimensional surface up to a set of dimension n-3. So what we prove is that in reality, you can do better than Caffarelli, you can cover with better than C1, but you have to, inside the singular points, the structure is more complicated. So there are these singular points, and within the singular points are subsets of these singular points, which are, let's say, less regular than all the singular points, than most of them. So most singular points can be covered by C11 upper surface, but then there is a small codimension 3 set in Rn, so this appears from dimension 3 on, where this is not true. And this is optimal. So we can build an example in dimension 3, where you have these very bad points inside the singular points. After that, we kept analyzing better the structure. We had a lot of development. So there, I will just mention that there is a work with Xavi Rossoton and Joachim Serra in 2020, and then 2 PhD students of ours, Franceschini and Zaton, 22. And what we know now is that Sing is contained in a C-infinity n-1 dimensional surface up to a set of dimension n-2. So so in reality, you can do better than what we did with Serra in terms of regularity, but there is a price to pay. Is n-2 now the let's say the exceptional set that you cannot cover? So up to throw away some lower dimensional part, you can actually show that you have a C-infinity surface that covers it. Okay, so this is one aspect of this problem about how regular is this singular set. Of course, this is not an end of the story, because you can still ask, okay, what about this exceptional set here, this exceptional set here? What can you say? Very little is known there. But let's say it's still, I would say, an advancement with respect to the C1 regularity. So now let me go on and let me go to point 2. So the point 2 was how common is the fact that the singular points and regular points have the same size, right? So I gave you this example in 2 dimensions when the singular set was a curve and the regular set was a union of 2 curves. How often this happens? So already many years ago, Scheffer in 1974 made a conjecture. So he conjectured that generically Sing should be empty. So in fact, Scheffer, roughly now almost 50 years ago, he conjectured that in reality the singular set is artificial. So it's there, but if I perturb a bit my boundary data, that should disappear. I should not see singular points. Okay, which is also natural if you think it just geometrically, right? I mean, you have your membrane, you lower it down, it touches the plane, and okay, you can have pathological solutions where you have these lines of singular points, but the idea is that the moment I lift a bit my boundary data, these points should disappear and I should just see nice sets of regular points. So there was Monod in 2003, he proved that n equal 2 is true. So in dimension 2, if you're in the plane, the conjecture is true. Then with Rossoton and Serra, we tried to find a way to attack it more in general in the higher dimension. So what we did was the following. We said, okay, we have our elastic membrane, right, which is attached to our boundary datum. And there is some contact region here, right? And now to have a notion of genericity, let's take a one parameter family of boundary data. So I have let ft be a family of functions from boundary of omega to r. And let's say that dt of ft is positive. So it means that my ft moves up and down. Okay, so they depend on a parameter t monotonically. So if t is higher, they go up. If t is lower, they go down. So t here is a parameter that varies, let's say, between -1 and 1. And then for each t, I solve my obstacle problem. So the obstacle problem will be Laplacian of ut equal characteristic of ut positive. Ut is a non-negative function. And then ut on the boundary of omega is equal to ft. Right? So this is my family of obstacle problems. And then the question is, what can I say about this family? So here we strongly exploit the fact that ft is positive. That dt of ft is positive because it means that our boundary data are ordered. And so since ft is increasing in t, then also ut is increasing in t, which means that if you take a solution and you take a higher t, then the solution will be higher. This is a maximum principle, okay? And now we exploited that, this having a one parameter family of solutions, we had to kind of make them to show that, if some solution does something, then a different solution has to do something else because they talk to each other. It's like is like having all these membranes that are ordered one above the other. So if I know something about the shape of one, I can say something about the shape of those above it, just because of ordering. So exploiting this, we proved, this is still the paper with Rossoton and Serra in 2020. We proved the following result, that for almost every t, so Lebesgue almost every t, if you look at the singular set for ut, this has Hausdorff n-4 dimensional measured 0. Which implies that seeing ut is empty for n less or equal than 4. So we could prove Scheffer conjecture in dimension 3 and 4 out of this. But in fact, it says more, right? It says that in every dimension, maybe the singular set could be as large as the regular set, but the moment you perturb a bit your data, in reality, the singular set is much smaller than the regular set. It's a codimension 3 set. So really, most points in the free boundary are like in Kinderler-Nuremberg. Okay, so this is really the picture you have at most points of the free boundary. And now, to conclude, I would like to discuss a bit the third point, which is very interesting, I think, because it's connected to other questions from physics. So let's say that I have a u from Rn into R, and then I have Laplacian u equal characteristic of u positive. So it's a global solution, u non-negative. Okay, so this is my setting. I want to understand solutions to this problem. Let rho be the characteristic of u positive. Okay, let me call it rho, this function. Then you see that the Laplacian of u is equal to rho. What does it mean, the following? It means this. So assume here that u is 0, let's say. This is my u equals 0. And then here, this is u positive. So where u is positive, rho is equal to 1. Okay, so rho is, you have to think of rho as a density, which is 1 where u is positive and 0 where u is 0. And now Laplacian u is equal to rho, which means that minus grad u is the gravitational force, generated by rho. So you think of rho as a distribution of mass. You solve Laplacian u equal rho. This is the gravitational potential generated by rho. And then minus grad u is the force generated by this rho. And now you say, okay, so this is the gravitational force. And what happens here inside the contact set, here inside? Here, u is 0. But if u is 0, grad u is 0. Or let's say minus grad u is 0, right? So inside the region where u is 0, so this means that inside u equals 0, there is no gravity. Right? So if I put a uniform distribution of charge, of mass, let's say, outside u equals 0, then inside u equals 0, this mass will generate no gravity because the gradient will be 0. Right? So this is a consequence of u being a global solution. So u being a global solution corresponds to say that this property, that when you put one outside the contact region, then inside there is no gravity. Okay? And so classifying global solution, so the problem that I told you, how global solution look like, can be reformulated in a different way. Question, which shapes can generate no gravity? So for which contact set I can have such a property? Because it looks like of a magical property, right? I mean, it doesn't look like this can happen that often. So this is a question that is rather long. The first result in this direction dates back to 1678. And this was Newton that proved that for n equal 3, u equals 0 is equal to a ball. So in what Newton proved in 1678 is no gravity inside a shell theorem. He proved that if it doesn't prove in this sense, if it's formulated differently. But what he proved is the following: that if you put a uniform distribution of mass on a sphere, then inside the sphere, this will generate no gravity. So a body that lives inside a sphere, if the mass is uniformly distributed on the sphere, then inside there is no gravity. And then, you know, a ball is just a union of spheres, and then you can deduce this formulation. So, so this is the first result by Newton. Then a bit more than 100 years later, Laplace and independently Ivory proved that for n equal 3, u equals 0 can be an ellipsoid. So if you take an ellipsoid shape, so I will use e to the ellipsoid e, capital E. Laplace and Avery showed that ellipsoids do not generate gravity the same way balls don't generate gravity. Okay, so if you take an ellipsoid and you put uniform charge outside, you will have no gravity inside. Here that you can have some convergence problem, of course, that you may be worried about, right? Because we are talking about infinite distribution of charges. But okay, these are just technical details. Don't worry about that. Everything can be taken care of. So ellipsoids are also admissible shapes to have no gravity. But now if you have ellipsoid, you can take limits of them. So what you can do is that you take in a Rn, right? This is you write Rn minus 1 and R. And then you take an ellipsoid and you center it with the boundary at the origin. So this is your ellipsoid. And then you start to rescale it and rescale it more. So you just dilate the ellipsoid and you rescale it. And by taking suitable limits of ellipsoid, you can generate, if you want, any paraboloid. So taking limits of ellipsoids also paraboloids that I will denote by P generate no gravity. Okay. So these three results, Newton, then Laplace Ivory, and then this limit, tells me that volts are possible contact sets, ellipsoids are possible contact sets, and paraboloids are possible contact sets of global solutions to the obstacle problem. So you can find global solutions that have this kind of contact sets. So these are examples of global solutions. Of course, you can also do trivial extensions, right? You take a function, a global solution, and you just make it constant in some fictitious variables. So of course, you can make them, you can add extra variables just for free, just make them constant. But then the question that you see once you have this kind of result is the converse. So what about the converse? So up to now, essentially this theorem is just a list of examples of global solutions. And then the question is, can I classify global solutions? So this the converse corresponds to the classifications. Classification. So the first result in 1931 is due to Davis. So what Davis proves is that if n equals 3 and u equals 0, so the contact region for u equals 0 is compact, then u equals 0 is an ellipsoid. So in 3 dimensions, the only possible contact region for global solutions are ellipsoids. You cannot have anything else. Sorry. Then almost 50 years, no, exactly 50 years later, 1981, Sakai proved that for n equal 2, u equals 0 is either an ellipsoid or a paraboloid. So in 2 dimensions, there is nothing else as contact regions besides ellipsoids and paraboloids. So the proof of Sakai is based on complex analysis, so it's really a 2-dimensional proof. Then 1986, Di Benedetto Friedman, and then Friedman Sakai proved that in every dimension, u equals 0 compact, n greater or equal than 3, then u equals 0 is an ellipsoid. So the first result by Di Benedetto and Friedman had some symmetry assumptions, and then Friedman Sakai did the full case. Okay, so these results cover in every dimension the compact case, but then you will ask, what about non-compact case? So what if u equals 0 is not a compact set? So in 1992, Shagolian conjectured that the result of Sakai, which says that there are only ellipsoid and paraboloid, should be true in every dimension. Not much happened actually until 2020. And in 2020, Eberl, Shagolian, and Weiss proved that n greater or equal than 6, then u equals 0 is either an ellipsoid or a paraboloid. Or again, I told you trivial extensions of them just by making them constant in fictitious variables. But the conjecture is true. And then finally, last year, with Eberl, myself, and Weiss, we proved the general case, which says that in every dimension, 3 and higher, ellipse and paraboloids are the only option of contact set. So all global solutions are classified, and we know all of them because these are just the ones generated by ellipsoid and paraboloids and nothing else. Okay. I think I took exactly all the time I wanted. Maybe just a couple of minutes to explain to you. This is maybe one thing that may be puzzling here is that the result was proved first in dimension 6 and higher, and then in dimension 3. In fact, here it is a kind of problem where, okay, n equal 2 is special, complex analysis, but then for large dimension is easier than low dimension. So in fact, 6 and higher is the easiest case. 4 and 5, once you understand how to deal with that, are not that difficult, not much more difficult than 6 and higher, but you have to be careful. And then for dimension 3 is way more difficult than all the remaining dimensions. So it's really a case where high dimension help. And I can tell you in one moment why. So in particular, why n, so why n greater or equal than 6. The reason is the following. So it's just a technical thing, but think of the following. Take a paraboloid in dimension 6 or higher, right? So this is Rn minus 1. This is R. And take a paraboloid. And look, so I told you that we're talking about solution to the obstacle problem, so you need to understand how the charge generated by the complement of paraboloid influences the inside and generates gravity. So let's just take instead, let me put the charge instead of putting inside, I put it out. Instead of putting it outside, I put it inside. So consider the following problem. Laplacian of W equal characteristic of the paraboloid, where this is my paraboloid. Okay. What is the solution to this problem? Well, what you will do is to say, okay, a solution should be taking W equal characteristic of P convolved with the green function of the Laplacian. So Laplacian of G is the delta. Let's say up to harmonic functions. So this would be the solution. But what is this? So the green function of the Laplacian is 1 over x to the m minus 2 up to constants. And so W of x will be the integral over the paraboloid of 1 over x minus y to the m minus 2 in dy. So this will be my solution up to constants. But now, if you do your computation carefully, you will see that this integral is finite if and only if n is greater or equal than 6. So it's only in a dimension that the indicator function of a paraboloid can be convolved with the green function of the Laplacian. While in the dimension, these integrals don't make sense. And this creates a lot of technical and non-trivial problems to make the proof work. So that's why high dimension helps. Okay, I think I took essentially all the time I had, so I will stop here, and I'm going to thank you for your attention.